Okay. Well, thank you, Joseph, and welcome to this afternoon session of today's seminars. We're very happy to have Geoff Penington from UC Berkeley, who's going to talk about black hole microstates versus the additivity conjectures. Geoff, whenever you're ready, feel free to start.
Okay, thanks very much. Yeah, great. So I'm going to be talking about this paper that I put out with Patrick Hayden in December of last year. And it's really saying that at least one of two, on the surface, very, very different things are true. So the first is what we call an extensive violation of the so-called additivity conjectures in quantum information exist. And the second one is that the Bechdel-Hawking entropy of a black hole can be almost entirely accounted for by what we call disentangled microstates. So obviously, given the topic of this conference, then possibility 2 will seem a lot more on sort of usual ground for the sort of things people might be talking about. I don't expect you to know what disentangled microstates are because it's a term we made up in this paper, but at least the flavor of the thing seems reasonable. Possibility 1 may seem very, very out of sort of people's wheelhouse. But hopefully, my aim for the talk is to sort of assume as little background in quantum information as possible, but at least tell you guys enough to motivate why this possibility 1 is something that QI people care about, and it's would be a significant thing from a quantum information point of view if it was true. And then I'll get on to talking about possibility 2. So yeah, the first half of this talk is going to have some really information-y quantum information, some quantum channel theory, but a lot of the technical details will actually not be at all important for the later half of the talk. But yeah, I'll try to signal the things that are actually going to be crucial. But one thing that we will definitely need is one of the most basic concepts in quantum information, which is a quantum channel, normally represented by this sort of math cal n, and all that is it's the sort of most general possible noisy evolution of a density matrix that you can have. So what can happen to a density matrix? What can we do to start with some input density matrix and end up with some output density matrix? Well, the first thing that you can do is you can just imagine adding in some extra system. So we start with some density matrix rho, and then we just tensor in some external system that's just in some unrelated state. Here I've written it as 0. I guess in general it can be any state psi or even a second density matrix, sigma or something. But we just go from the state rho to rho tensor something else. So that's one thing that can happen. Second thing that can happen, obviously, is just unitary evolution. That's what we normally think of as evolution in quantum mechanics, sort of noiseless evolution. So you can have sort of the state density matrix rho go to u rho u dagger for any unitary u. And then the final thing we can do is we can just decide that there's some subsystem that we don't care about. Maybe some subsystem after our unitary evolution is describing the state of some photons that are escaping the system or something like that. And we just decide that that's not something we're going to keep track of anymore. We're just going to throw that away. Okay, and the way this is described, obviously, is by what's called a partial trace. So we have a density matrix, 2 subsystems, and then we just throw away one of the subsystems by tracing out over it, and that gives us some reduced state, normally given by the same symbol, rho, but with only one index this time. Okay, it turns out this is the sort of most general thing that can happen to a density matrix, most general sort of noisy evolution we can have. So any quantum channel can always be written as a combination of these 3 things. First, we tensor in some external system. Then we have some unitary evolution that can interact our initial state rho with that external system. And then finally, we throw away some subsystem as the resulting output. And I really encourage, by the way, people to ask any questions you have about any of this stuff. I'm aware that I'm talking about things that maybe is out of people's wheelhouse. So if I assume knowledge of anything, then it's not clear to you, then please shout.
Okay, so just to make sure I understand, so
Yep.
a quantum channel is just a map between some density matrix in some Hilbert space to some other
Yep.
density matrix in some possibly different Hilbert space,
Yep.
and the most general relation between the two is what you wrote in this end of row.
Yeah, exactly. So one definition is what I just gave. An equivalent definition is that it's what's called, it needs to map density matrices to density matrices. So that's what's called a positive trace preserving map. But it also needs that if I act with it on, say, half of an entangled state, then it still needs to map that to a well-defined density matrix, so a positive matrix. And that's called being completely positive. So another definition is a quantum channel is just an arbitrary, completely positive trace preserving map, essentially something that maps density matrices. But there's a theorem that says the most general such map can always be written in this form.
I see. Thanks.
Okay.
I have a question.
Yep.
So step 3, when you throw away a subsystem, it can be any subsystem, nothing to do with the external system which you added.
No. In general, density matrix, for a quantum channel, the output system can be different from the input system. So the thing you throw away is unrelated to the thing you added. Yep. Okay, great. Thanks very much for those 2 questions. Very helpful. Okay, so there's another thing I want to introduce, which is called the mutual information between 2 subsystems of a quantum state rho AB. Okay, so what is this? It's just defined by a simple formula. It's the density matrix, the von Neumann entropy of the density matrix on A. So von Neumann entropy, remember, if anyone's forgotten, it's just minus trace of rho log rho, plus the entropy of subsystem B minus the entropy of the combined system rho AB. Okay, so there's another maybe more intuitive way to write this down, which is it's the density matrix of the state that's just a product of the reduced state on A with the reduced state on B minus the entropy of the full density matrix AB. In other words, it's the decrease in entropy that you have from remembering that there's correlation between the state on A and the state on B, or maybe there's entanglement, stuff like that, right? So it's the decrease in entropy from on the one hand, just having the product state with the right reduced density matrices, and on the other hand, having the full correlated state rho AB. Okay, so this is something that's always positive for a start, or is non-negative. So just to give some very simple examples, for a product state, it's just 0, right? There's no, you don't get any information about A by looking at B or vice versa. For 2, say, maximally correlated classical bits, so in other words, for a density matrix that looks like sort of a half, tensored with both subsystems being the state 0, plus probability a half that they're both in the state 1, right? So this is sort of maximal classical correlation. Then that has a mutual information of 1 between the 2 systems. And the final case, just a stupid example as well, is if I have a bell pair. So I have rather than having classical correlation, I now have quantum entanglement. And I have a superposition of the state 0, 0 plus the state 1, 1. Then that actually has a mutual information of 2 between the 2 systems. So in this classical correlated case, then the entropy of A, just subsystem A, it's a random bit, so that's 1. Entropy of B is also 1, and the combined entropy is 1 because they're both in the same state. But in bell pair, you have something even more remarkable than that. You have an entropy of 1 for each of the 2 subsystems, but the entropy of the overall pure state is 0, right? It's in a pure state. So that gives us this super classical mutual information between the 2 sides. Okay, so those 2 things were just sort of quantum information background that we're going to need. But we're now going to get to the sort of the big question that originally motivated these sort of additivity conjectures. And it's actually in many ways the sort of single oldest question that can meaningfully be called quantum information. And it was actually posed by Claude Shannon himself, the person who invented classical information theory, and it's just a sort of quantum generalization of what's called the noisy channel coding theorem, one of the two basic theorems in classical information theory. So what it is that we imagine there's two people, Alice and Bob, and Alice wants to send a message to Bob. She just wants to send a classical message, but it turns out that she rather than just having the ability to send Bob the message through a classical channel, she can send it through some general sort of quantum channel. She can send a photon to Bob, or she can do something, but there's some noise en route. So it's the process of sending a message from Alice to Bob is described by some noisy quantum channel.
I'm sorry. I'm not sure I understand the difference between a classical and a. I guess what you just explained was a quantum channel.
What I just explained was a quantum channel. A classical channel. A classical channel would just be some conditional probability, basically p of y given x, that tells you if you have some input x, then some input probability distribution p of x, then it tells you what the output probability distribution p of y received by Bob. Okay, so that can be thought of as a special case of a quantum channel where everything is diagonal, basically.
I see. So if I just want to model the classical things, I just take diagonal density matrices and then I'm fine.
Exactly. And you take a channel that preserves diagonal density matrices and so on, and then yeah.
Okay, perfect. Thanks.
Great. Okay. So it turns out that this is a sort of the question of how much information, how large a message Alice can send through one use of a quantum channel. Turns out it's kind of messy and hard. These days, we can sort of answer it, but that's 21st century quantum information theory. What Claude Shannon asked about, both classically and quantum mechanically, is let's suppose instead we have some large number of uses of the same channel. We assume that there's no memory or anything, so each time we use the channel, we just have the same channel. We can just input a density matrix each time. The process is noisy, so what Bob receives is kind of random, but it's just a memoryless thing, so we can just send a quantum state through a different channel lots and lots of times. And then we consider the limit where the number of uses of that channel that Alice is allowed to use tends to infinity. So we consider some large number of uses, and then we want to ask the question of what's the rate at which Alice can send classical information through that channel, i.e. the number of classical bits sent per channel use and the limit of a large number of channel uses. Okay, so just a formal way to state that is that we want the number of separate messages that Alice has to be able to successfully send to be to be 2 to the n times this rate r. Okay, in other words, n times r bits through n uses of the channel, and then we're going to take n to be really, really, really big. Okay, so what's the most general protocol that Alice can use to send this message? Well, essentially, she depending on the message she wants to send, she's going to prepare some different density matrix rho I. In practice, she's going to want to prepare some pure state rather than a noisy state, but she prepares some state rho I, then she sends that through the large number of copies of this channel n. So then Bob receives some output state that's just n copies of the channel applied to that state rho I. And then Bob goes, okay, I've just received this quantum state. I want to learn this classical message that Alice sent. And so what he does is just do a measurement on this output state. And he wants to be able to do a measurement that can sort of accurately determine what I was. Okay, so basically he needs all these different output states with this noisy evolution applied to this input state rho I to all be roughly orthogonal states, so that you can distinguish them all successfully through a measurement. Okay, any questions about that? About what the setup is, what the question that we're asking about, why anyone would care about such a question? Okay, I'm going to assume that it's clear to everyone now. Okay, so with this mutual information that I introduced a few minutes ago, one thing that's easy to see is that there needs to be, at the end of the day, a large mutual information between the initial classical message that Alice wanted to send and Bob's measurement outcome, the classical message that Bob receives, right? They need to be the same thing. So if Alice just picks a random classical message to send, then basically the mutual information between her input and the classical output Bob gets after his measurement needs to be equal to just R times N, right? Because that's the number of classical bits that need to be maximally correlated between the message Alex sends and Bob's successful reception of that classical message. But there's a basic inequality about von Neumann entropies that in this context basically says that the classical correlation between Alice's message I and Bob's measurement outcome has to be less than or equal to the mutual information between Alice's message I and the state that Bob, the quantum state that Bob receives that he then uses to create that measurement outcome, to do a measurement on to get his final answer. Okay, so roughly speaking, the amount of, like if the state, the noisy evolution applied to rho I doesn't have any correlation with the initial input I that Alice chose, if it doesn't depend on I, then whatever measurement Bob does, he can't learn anything about I. Okay, so that's intuitively what this inequality is saying. This gives us an upper bound on how many different messages can successfully be sent. Namely that it has to be less than the mutual information between these noisy channels acting on rho I and the classical message I that Alice originally wanted. Also, it turns out, I'm not going to explain why this is true, but given any set of rho I's that are set inputs to some number of channel uses, then in general this inequality is not saturated. Okay, it's a strict inequality, but if we're allowed to increase the number of channel uses, so rather than just using n channel uses, we have some much larger number of channel uses, then it turns out you can, given any mutual information like this for any set of inputs rho I, then we can always find some code for some much larger number of channel inputs that achieves the rate given by 1 over the original number of channel uses times the mutual information between the output Bob receives and Alice's original classical message. Okay, so we've now shown that the rate is always upper bounded by the mutual information for some input. Moreover, for any input, we can find some way of sending information from Alice to Bob that roughly achieves that mutual information. So from there, we can immediately see this sort of famous theorem by Halevo, Schumacher, and Westland that essentially answers Shannon's question. It says that the maximum rate that Alice can send information to Bob per use of the channel is just given by the max over sort of ensembles, sets of rho I on m inputs to the channel times the mutual information for that ensemble rho I times 1 over the number of channel uses, and then we need to take a supremum over the number of channel uses that we needed. I'm hearing some phone ringing in the background. Is that me or is that not? I don't think it's me. Okay.
At the moment, it seems that you're the only one who's unmuted.
Okay. I don't know. Okay, seems to be gone. Great. So this is a thing. So it's often rewritten. So with this supremum over all inputs to the channel, we often just call, it's like some function of the channel itself, right? That's the only thing it depends on. So we're maximizing the input channel. It only depends on what the channel is. So this is often called the so-called Halevo information of the channel. It's given this letter chi. Okay, so there's this formula for the maximum rate at which you can send classical information per use for a quantum channel. It's just given by the supremum over number of channel inputs times the m times 1 over m times the the Halevo information for m copies of that quantum channel. Okay, so that at some level just answers the question of how much information can we send through a quantum channel. But there's a bit of a problem, which is that we have this supremum over m, this supremum over number of channel uses that we need to actually calculate the answer. And obviously, m can be arbitrarily large. It can, can be any integer from 1 to infinity. And so the answer to this formula can never actually just be explicitly computed in practice, right? We could check all inputs to sort of 100 copies of a channel or 1 million copies of a channel or something like that, and we could find the largest mutual information we can find and say, okay, that's the Halevo information for that number of inputs, and get a rate of like 10. But maybe if we thought to consider like 1 billion copies of the channel and then look for maximizing overall inputs of that mutual information, then maybe we could get some even larger number. So we could never actually compute what the answer is for the maximum rate that we can send stuff through this channel. So it turns out that if we had a classical channel, so in sort of classical Shannon theory, then this isn't actually a problem at all. Because this supremum over the number of channel inputs times 1 over m times the Halevo information is actually just the same answer you get by just maximizing over one channel input and forgetting about the supremum over m entirely. And the reason for that is there's this thing called additivity that means this sort of maximizing over inputs of the mutual information on the tensor product of two channels is just equal to the sum of the maximizing over inputs on the original channel. So if I have, say, 10 copies of the channel n, then the Halevo information is just 10 times the Halevo information of one copy of the channel. Halevo information of one copy of channel is just something we can explicitly compute. And so this means that we can just actually work out the maximum rate at which we can send information to this channel. So back in the sort of 90s, when people started really seriously thinking about quantum Shannon theory, there was a very natural question, which is this also true for quantum channels as well? Right? When we write down this formula where we maximize over m and consider m copies of a quantum channel, do we need to do that, or can we just get away with only considering one copy? So this was sort of super important to people for a couple of reasons. One is that it would mean you could actually compute a quantum capacity of the channel. And the other thing is that it would basically tell us, because of the way this proof works, if we know that you only need to consider one copy of a channel, then it would tell us that these row i's, these inputs that Alice uses to send stuff to Bob, never actually need to be entangled between the different copies of the channel. So Alice can always, for each I, just have some product of a state like psi1i to the input to channel 1, psi2i for input to channel 3, and so on. She doesn't need to consider inputs that are entangled between the different channel uses. Okay, so this is obviously the big question. But then in the mid-2000s, then Matt Hastings actually answered it, and he showed that actually the answer is no. So quantum channels aren't like classical channels. You can't get away with only considering one channel use. Actually, you can have violations, and you do need to do this supremum over m. But he also found something wrong. His counterexamples were sort of not very interesting, because basically the largest counterexamples that his method came up with were violations on the order of like 1 bit. In fact, they were roughly half a bit or something, half a qubit. So in other words, what he found was that if you have a channel that naively has a capacity of sending 100 bits per channel use, maybe the real capacity is 100.5 bits, but who really cares about that, right? And no matter how big you made the input system, maybe you've made something that has a capacity of like 1 million bits, right? Maybe you look at a large number of copies of the channel, and so the capacity is already 1 million bits, then you only get a 1 bit violation. Who cares about 1 bit on top of 1 million bits? So what this sort of, if you only have these sort of violations, then all you have to do is consider m like relatively big, maybe m 100,000 or whatever, and you'll know that you have a pretty accurate estimate of the capacity of the channel. Maybe you're off by a tiny amount, but you're off by an order 1 over m. Okay, so that's the current state of affairs. Over the last 15 years or so, people in quantum information have sort of tried pretty hard to make these violations bigger. But whatever anyone does, they've basically only been able to get this sort of 1-bit violation or something like that. But there's one sort of piece of the story that I haven't said yet, which is about how Hastings actually found these violations of additivity. Because it turns out he didn't actually explicitly look for violations of additivity of this Halevo information. Instead, what he looked for is violations of additivity of what's called minimum output entropy. So this is actually sort of a simpler definition in many ways. So if you got lost somewhere in the stuff about mutual informations and so on, try and pay attention to this definition right here, because it turns out that that's going to be the relevant one for the rest of the talk. Everything above was just sort of motivation. So what is this? Well, the minimum output entropy of a channel is just you consider all possible inputs rho to a channel, and then you look for the one that has the smallest output entropy, in other words, the smallest von Neumann entropy of n acting on rho. Okay? And then you consider the following question, which is if I have 2 copies of my channel n, or a copy of channel n and channel m maybe, and I minimize the output entropy over all inputs to that channel, can that be smaller than just 2 times the minimum output entropy of 1 copy of the channel? In other words, is this minimization over multiple copies of the channel always achieved by a product of a state on channel input to channel 1 and input to channel 2, or can using some sort of entangled input allow us to get an even smaller output entropy? Okay, so it had been shown by Peter Shaw that this is actually equivalent to the additivity of the Halevo information that was discussed above. And more than that, like having the size of the violations are the same in each case. Okay, so if we can find a 1-bit violation of additivity of minimum output entropy, that corresponds to a 1-bit violation of additivity of Halevo. If we can find a really big violation of additivity of minimum output entropy, that would be big violations of Halevo, big violations of classical capacities. The sort of simple classical capacity formula wouldn't even be close to being right. Okay, so now finally ready to state what this possibility 1 is. Essentially, it's that extensive violations, in other words, it's violations that grow extensively with the size of your input system of additivity of minimum output entropy are possible and exist. Okay, so if we have n input qubits, then we can find some channel that has a violation of minimum output entropy that's order n. We can find some family of channels that grows with n. The violations also grow with n. Okay. Any questions about all of that? Because that's the end of the very, very quantum information section of my talk. Please shout out if anything's unclear.
Yeah, sorry, I think I got slightly lost. So just looking at this formula that you told us to remember. So here, what you're varying is the input rho, or you're varying the channel so as?
Yeah, great. So this is a property of the channel that is found by minimizing over all rows that it inputs the channel.
I see. So on the right-hand side, I'm putting some rho in some Hilbert space, and on the left-hand side, I'm putting some rho in
two copies of the Hilbert space. Yeah.
I see. So these rows live in totally different Hilbert spaces.
Yeah.
And n is fixed.
N is a fixed channel, exactly. So for example, yeah. So let me just make just a try example. Why should we know that this left-hand side is less than or equal to the right-hand side? Well, because we can always, if we have whatever row minimizes the right-hand side, on the left-hand side, we can just consider the tensor product of two copies of that row, right? And then that's a product state, so its entropy is just twice the entropy of the entropy on the right-hand side. And so that at least, saturates that inequality. The question is whether it's a strict inequality, whether we can consider some other row that gets even smaller.
Okay, thanks.
Great.
There is another question by Andrea.
Yeah, I think I missed the point. So when you go from the Halevo to the minimum output entropy, is the statement that the additivity conjectures are at the same footing, or is one a subset of? But because the two entropies are not the same, right?
They're on the surface. They're very different questions about additivity. But it just turns out that you can prove, you can look up this paper by Peter Shaw. It's not terribly hard, but I don't want to get into it here. You can prove that if you have, if one of them is true, the other's true, and the size of the violations in each case is the same.
So it goes
that's a very
both ways.
non-trivial statement. Yeah, it goes both directions. It's an equivalent. Okay. Any other questions? Hand up. No. Okay. Great. Okay, so now move on to some quantum gravity. So possibility 2. And to do that, big thing I'm going to need to introduce is what's called the Ryo-Takayanagi formula, which should be a lot more familiar to people than quantum Shannon theory, but I'll introduce it anyway. So this is a rule for computing the entanglement entropy of some sort of boundary subregion in ADS-CFT. And there's various more and less general versions of this, but for our version, for our purpose, it will be just to just say the most basic original version, which is that for static states or time symmetric states, it's just given by this entanglement entropy S of B is just given by the area divided by 4 times Newton's constant of the minimal area surface that's what's called homologous to this boundary region B. Okay, in other words, that it's sort of anchored on the boundary region B. Homologous has some more technical constraints, but that's good enough. Like the boundary of this surface is the boundary of B. Here and here. Okay. So, for example, one can consider a black hole, and one can then consider a boundary region B that's maybe slightly less than half of the boundary. And then the sort of minimal surface, homologous to that, sort of goes into the bulk. It's the surface shown in green, and then it goes round the side of the black hole, and then it goes out to the boundary again the other side. Okay. It turns out this formula is sort of expected to be true both for thermal black holes, like the thermal field double state or something, and for sort of typical pure black hole microstates. So for some particular microstate, as long as it's a typical state in within that energy band, for example, then by the eigenstate thermalization hypothesis, it should have exactly the same entropy. Okay, and by the RT formula, assuming it looks like a black hole outside the horizon and doesn't have anything weird happening outside the horizon. Okay, we can also consider a different entropy. We can consider a two-sided black hole, so a thermal field double state. And we can consider the entropy, we can consider a copy of this boundary region B on the left boundary and a copy of it on the right boundary.
Sorry, can I have a question about the previous, the pure typical state? So now if I make this region B to be almost the entire boundary, so then I have some tiny contribution from the boundary, and then the thermal entropy, which makes perfect sense if I'm in a thermal ensemble. But for a pure state, even if typical, I would expect that part to vanish, right? Yes. Is this a puzzle?
No, that just comes from the fact that we have this condition of being homologous to the boundary. So if I have some pure state, let's say it was a black hole formed from collapse or something that has been allowed to sit there for a long time, and we believe in that black hole formed from collapse, then so let me make my boundary region B.
But not a typical state, right? The collapsing, the black hole.
Okay, it should be true for the typical state because of the eigenstate thermalization hypothesis, but it's also true for any state that looks like a black hole outside its horizon and has has trivial homology, right? So a two-sided black hole, then a surface that looks like this is not homologous to sort of almost all the boundary. And the reason for that is that there's a wormhole that goes and connects out to some different boundary. But if I just had something that looked like a black hole formed from collapse, or like a black hole that ends on some drain in the interior or something like that, then it is homologous to this almost entirety of the boundary because the space-time interior ends. It doesn't go off to some second asymptotic boundary. Is that clear?
Roughly.
So, I have a related question which relates to microstates. So microstates have horizons. I mean, if Okay. The first comment is that this formula presumably holds where when semi-classical gravity is correct in the regions through which the surface goes through, I understand. And
Sure.
for microstate, I don't expect they have any horizon. So what does the homology constraint give in that case? I should.
Yeah, look, let's say, for example, you replace the horizon by some brane or some non-semi-classical object, then you can still say that the space-time ends there, and so you can still define a homology constraint by just saying that you're allowed to have some boundary where the space-time is ending on some end of the world brane or whatever it might be. Yeah, it's the homology constraint is really just about disallowing something where it has some semi-classical connectedness to a second asymptotic boundary, right? So in this two-sided case, if you looked at almost all the boundary on the left, then this little thing is not homologous to all the boundary on the left, and the reason is that there's this second asymptotic boundary over here that's connected. So I would say as long as you don't have a second asymptotic boundary, then the homology constraint is basically trivial. And it has to be because the bond nominal entropy of two complementary regions for a pure thing is zero.
Yeah, I understand. I guess my comment was more about, if I had a microstate which was smooth everywhere and has no horizon, what?
Then I think it's clear.
Right.
If you have some microstate geometry that's like smooth everywhere, then I think it's clear that the homology constraint is satisfied, right? Like there won't be any boundary. It's just caps off with some smooth geometry, and it's clear that the homology constraint is satisfied.
That's right. Okay. Yeah.
Okay. Great. But in this case, we're considering slightly less than half the boundary, and so the sort of minimal surface goes to on the same side of the black hole as the boundary region. We don't have to worry about these homology issues at all. Okay. Great. But what we are going to consider is a two-sided black hole, thermofield double state, and then we're going to consider the entropy of B left and B right, okay? S of B left, B right. So we have the left boundary thing and the right boundary thing. And again, we want to just consider the minimal area surface homologous to both of those two things at once, right? So a naive answer might be, well, it's just going to be surface on the left side of the wormhole that looks like that, and surface on the right side of the wormhole that looks the same. Okay, but it turns out for the case of interest, that's actually not true. There's actually a smaller surface. And the smaller surface does is it just sort of goes through the black hole horizon. So it goes from the left boundary down to the black hole horizon, goes through the Einstein-Rosen bridge, sort of shown it going through here, and then it comes out to the other right boundary. So it connects the two boundaries together. It turns out so I called this area going around the side of the black hole A0 before. I'm going to call the area of these surfaces that just goes to the black hole horizon A1. Turns out A1 is smaller than A0, and so having this thing where it goes through the wormhole is preferential to just having separate surfaces on each side. Okay, so this entropy of B left, B right in the two-sided case is equal to 2A1 over 14. Okay, so now I'm going to make a few assumptions, and we're going to see an extensive violation of additivity, and then we're going to try and make those assumptions a bit weaker and actually make them realistic. So for the moment, just go with me on these assumptions, even if you obviously don't believe them, and then we'll weaken them a bit later.
And so your calculation is done at t equal to 0, or are you allowed to time evolve, or and what happens?
So for the thermofield double state, I was considering t equal to 0. For the one-sided case, it doesn't really matter if you have time evolution, because this thing stays outside the
the reason I'm asking is that sometimes the length of the surface that goes through the wormhole can grow with time if you evolve.
Yes, the one going through the wormhole, we need to consider t equals 0. This is for the specific case of the thermofield double state at t equals 0.
Okay, perfect.
Okay, so let's suppose we've managed to make some subspace of states. We call this a code subspace, but it just means a subspace of states in the CFT that's going to contain all black hole microstates at some given energy. Okay? And it's not going to contain anything else. It's just going to contain all the black hole microstates. In particular, I'm going to make two very strong assumptions.
I don't understand
Yep.
actually, because I used to think that the code subspace was the same thing as the small Hilbert space that Papadodimas and Raju were talking about.
You can consider a code subspace just means some subspace of states. So you can consider all sorts of code subspaces. In this case, I'm considering one that's meant to include all states in the CFT within some energy band, like all black hole microstates within some energy window.
Oh, the restriction comes from the energy band. Okay, thanks.
Yeah, exactly. So we're only considering states of some energy. And I'm going to assume two things for the moment, which, it's sort of obvious these two things are true, as stated. Well, I'm going to assume, firstly, that every pure state in this code subspace is just a typical black hole microstate in the sense described above, i.e. it has this S of B is just given by this surface A naught over 4G. Okay, and the second thing I'm going to assume is that we can build an approximation of the thermofield double state out of a tensor product of two copies of this subspace. Okay, so formally, the thermofield double state, I think I wrote it here, right? It has support on all energy eigenstates of arbitrary energies. So we're never going to be able to exactly make the thermofield double state, but if we have a wide enough energy window that's completely small compared to the actual energy of the black hole, then we can make a very, very good approximation of this thermofield double state. Okay, so let's say we have these two strong assumptions, then I claim that would imply an extensive violation of additivity of minimum output.
Sorry, do you need every pure state? I mean, they would be
Yes,
a
I
major
do.
zero.
Yeah, so I will get to that in a minute, but for the moment, let's just see why these assumptions would lead to a violation of additivity. Okay, so what we're going to do is we're going to define N to take as input states in this code subspace of CFT states, and then the output is just going to be the reduced state of those density matrix on the boundary subregion B. Okay, so in other words, the channel N takes in some state in the code subspace. It embeds it in the larger CFT Hilbert space, but you can sort of forget about that. Basically, it just takes in the state in the code subspace and then traces out the part of the boundary that we want to throw away and get some reduced state on big B. Obviously, to define this, you need to UV regulate your CFT and stuff, but we can do that in a pretty well defined way. Okay, so by this first assumption that every pure state in H code is just a typical black hole microstate, then we have that the minimum output entropy of this channel, in other words, the minimum S of B for any state in this code subspace, is just given by A naught over 4G. Okay? But by assumption 2, with 2 copies of the channel, then we can make a thermofield double state. Okay? And the minimum output entropy of 2 copies of the channel if your input is the thermofield double state is just given by this thing. It's the output entropy of the 2 copies, so S of BR, and that's just equal to 2 times A1 over 4G, which I claimed is strictly smaller than 2 times A0 over 4G. Okay, so we have a minimum output entropy for 2 copies of the channel that would be order 1 over G newtons smaller than the minimum output entropy for 1 copy of the channel. This would be an extensive violation of additivity just by considering the limit where G newton goes to 0. Okay. Any questions about how that would work given those 2 assumptions? I'm gonna now talk about obviously these assumptions are pretty non-trivial.
So just to, I guess, shoot ahead, if there exists any fuzzball pure state in your in your CFT in that energy band, then the minimum would just be 0 because the
minimum wouldn't. So even for a fuzzball, the output entropy will not be 0. right? Because
it's
even a
entanglement.
fuzzball will have entanglement between the left and right, the two halves of this single boundary. But a fuzzball
But
could
it would
easily
be-
have a much smaller entanglement entropy than A naught. So yes,
And
definitely.
then I take, I see, and then if I take 2 copies of the fuzzball, and then possibly the minimum for the 2 copies,
Two copies could be smaller than, or it could not be smaller.
would be order 1 away from the.
Yeah, that would be the way to avoid the violation. So yeah, let me now.
Yeah,
So
before you
there's
go,
sorry.
can I ask a quick question? You're calling this an extensive violation, and I'm just want to get a sense of that. I mean, both of those quantities just above are UV divergent. They're formally infinite.
Yeah.
Whereas the difference between them is of the order of the black hole entropy, which seems like an impressively big number, but compared to infinity, it's still a small number. So
yeah, that's a completely fair comment. My answer would be is what you would want to do is just regulate, IR cutoff the bulk, UV cutoff the CFT at some scale that's like far above the black hole scale.
Yeah.
And then we want to say that that doesn't mess up we can do that without messing up the black hole physics. And then then we have some cutoff scale, but we can,
what would an order 1 violation have been in your counting in this? Would it have been
literally 1 qubit?
1 qubit? I see.
Yeah.
Okay.
So this is definitely much bigger than that.
Okay.
In the sense that it's extensive. Yeah, it's extensive with a very small parameter in front of it, right? If we wanted to regulate a CFT Hilbert space for some finite dimensional thing, then it will be, e to the order 1 over g, but with some huge prefactor in front of the 1 over g, right? That lets us regulate it at some very large cutoff scale. But that's still fine. That just means there's some very small prefactor in front of the order n, but it's still extensive.
Okay.
Certainly, it's much bigger than 1 qubit.
And sorry, I have a related question. So at the beginning, when you introduce these channels and so on, you're talking about mutual information, which is UV finite. Could you rephrase this whole discussion or this whole puzzle you're presenting in terms of some quantity that
in terms of a LEGO information? Yes, that should be possible. I see no reason why it's possible. We didn't do that just because you can regulate things, and I don't think it's the most strongest, most questionable stuff in what we do. But I expect you could define everything in terms of mutual information. Okay. Right. So obviously these two assumptions, assumption 1 and assumption 2, are very, very strong, right? So let's just try to build a code subspace that satisfies both of those assumptions. So the first thing we might want to try is sort of what I said before. Let's just consider all states to be in some code subspace so long as they lie in some energy window. Again, we need to make that energy window wide enough to be able to approximate the thermal field double. Turns out the size needs to be order 1 over square root g. So it's like pretty wide energy window, but much smaller than the energies of black holes we're talking about. So narrow compared to that. So if we have that be our code subspace, just the span of eigenstates in that energy window, then assumption 2 clearly holds, right? We can approximate the thermal field double to very high accuracy. But on the other hand, assumption 1 clearly doesn't, right? Within that pretty wide energy window, there'll be all sorts of non-black hole states. Just states that don't look like a black hole at all. States, for example, that have a load of radiation out near the boundary or something like that. So we don't know, have good control over the minimum output entropy. We don't really know what's going on. But that's not the only thing we can do. We can sort of take that code subspace, and then we can throw away some states in it and make a smaller code subspace, but still hope to be able to approximate the thermal field double state with 2 copies of it. Okay, so the most obvious thing to do is just to look for states within our code subspace that have S of this boundary subregion B less than or equal to A1 over 4G, and then just throw them away from the code subspace. Just look at the orthogonal complement of that within the code subspace. And because the thermal field double state is so entangled, then we can throw away an awful lot of such states and still be able to make a very, very good approximation to the thermal field double state. In fact, as long as we throw away less than order e to the s states, we'll still be able to make a very good approximation to the thermally filled double state. So really, there's only one of two things that can happen. Either we throw away some states that have small s of b, and we keep throwing away, and at some point we just run out of states to throw away because we have a minimum output entropy that's like strictly larger at leading order than A1 over 4. It's one possibility. And in that case, clearly we found a violation of extensive violation of additivity, so we found possibility 1. The second option, of course, is that we do find order e to the s orthonormal states by throwing them away one by one, looking at the orthogonal complement, such that for every one of those states, we have this s of b be less than or equal to A1 over 4. So that then is possibility 2, that there's some orthonormal state of disentangled microstates. By disentangled microstates, just mean that this entropy of half of the boundary is less than this particular value A1 over 4g. And we have enough of them that we can account for the entire Bekenstein-Hawkey entropy up to at most some subleading order 1 correction, right? This really has to be order e to the s. It's not e to the order s, it's order e to the s. And they really do have to be exactly orthonormal. This is really a basis of microstate, or very, very close to a basis. Okay, so why should you care about possibility 2? Well, because strongly suggests that you have this sort of orthonormal basis in microstates that have some structure at or outside the horizon. So obviously, you guys could say this is fuzzballs, other people would say firewalls, whatever. There needs to be something going on at the horizon. Let me give an argument for that. Again, it's going to involve some assumptions, but something needs to be true along those lines. Okay.
Can I just interrupt just for a second and just to let you know that you're at your 50-minute mark?
Okay, great. Okay, so let's assume the following things. The first is some people might say that not all states in ADS-CFT even have a bulk interpretation tool of any kind, semi-classical or otherwise. Okay, so I'm going to assume that it has some sort of bulk interpretation. I'm going to assume as well that these microstates obey the RT formula or the quantum generalization of it, the QES prescription. Maybe with some non-semi-classical stuff, you need that to be suitably generalized in some way, but going to assume that the QES prescription basically behaves normally. Assumption 2 is that outside the horizon, this microstate is going to look like an ADS Schwarzschild black hole. And finally, going to assume that it has some smooth geometry at the horizon itself. I claim that these 3 assumptions are sufficient. Okay, I'm not going to assume anything, by the way, about the interior. The interior can do whatever crazy things it wants. All I'm going to assume is that there's a smooth horizon. I claim that that's enough to show that the entropy of this half of the boundary, S of B, has to be bigger than this A1 over 4G. In other words, this can't be a disentangled microstate. The disentangled microstates have to break one of these assumptions. Okay, so why is that? Well, it's a pretty simple argument. Let's assume that we have some microstate that has some smooth horizon, but maybe inside the smooth horizon, some wacky, crazy stuff happens. There's some weird geometry. And then maybe our RT surface, our quantum extremal surface, rather than going around the outside of the black hole, so rather than doing this, which is sort of the naive thing we assume we know happens typically, then for this particular microstate, it does some crazy stuff in the interior instead. We don't have any control over what it does in the interior, but what we can do is just look at the exterior part of it. So just sort of erase all of the exterior and just look at the part of this surface that's outside the black hole until it hits the horizon. Turns out that exterior part alone has to have area bigger than A1 over 4G, because sort of by definition, the area A1 is the smallest area surface going from this boundary region big B to the horizon. Okay, that's like sort of how we constructed it, right? With the smallest surface going through the horizon from one side to the other, that's just 2 copies of the smallest surface going from the boundary to the horizon. This is a bit loose, by the way, because I've sort of not really defined RT surfaces properly. And really for dynamical spacetimes, they're not actually the smallest area surface. But it is true, so trust me on that. You can use what's called Maximin arguments to say essentially the thing I just said. That you can just look at the exterior part of this RT surface, and it already has to have area bigger than or equal to A1. Okay, so that's an argument for why you can't have a disentangled microstate with a smooth horizon. On the other hand, of course, let's say we do have structure at the horizon. So a simple example is just you imagine you have some end of the world grain at the bifurcation surface. Then the RT formula does say exactly the RT formula says that surface is allowed to be anchored on the grain, and it will in fact be exactly the surface A1 going from the boundary down to the horizon, and then just ending at that end of the world grain. So this is exactly the sort of entropy we would expect if we have some kind of structure that's replacing the horizon or at the horizon. On the other hand, if we time evolve these states, we should expect that they sort of stop having this small entropy. If you time evolve some disentangled states, in general, it will thermalize, its entanglement entropy will increase. And so this doesn't tell us that the state continues to not have a horizon when you time evolve it into the future. Okay, so you can have something like a Z2 quotient of a two-sided black hole with Hartmann-Martinez state, where you just sort of have an end of the world grain sitting here. That's fine, or the RP3 Geon, for example. There's all those sort of things that do have a horizon, just not anything behind a bifurcation surface, are still consistent with that. On the other hand, in fuzzball proposal, you'd normally say that there's no horizon at all at any time, but you can still have the fuzzball itself thermalizing, so you can have an equivalent explanation in my story. I'm just saying that it doesn't prove that the horizon ever develops. It just shows that at some point you have structure at the horizon. Yeah, let me very briefly talk about tensor networks, but really, this is sort of everything I wanted to say. So yeah, another reason to think that these disentangled microstates exist rather than extensive violations of additivity is tensor network toy models of ADS-CFT. So the sort of traditional toy model of a typical black hole microstate in a tensor network toy model is just some big sort of hard random tensor sitting in the center of the network. But we can also consider replacing that big hard random tensor by just a product of two individual tensors. And in that case, the sort of minimal cut through the tensor network can sort of jump through the gap between those tensors, and you end up with an entropy for SB that it looks exactly like this A1 over 4G. So certainly they suggest that the answer is possibility 2 rather than possibility 1. But on the other hand, tensor networks are a pretty crude toy model. Yeah, they have no sub-ADS locality, they have no real notion of energy, various other things. So I wouldn't take that as particularly compelling evidence in favor of possibility 2, but I do think it's some evidence. So yeah, that's basically all I have to say. I think it's a genuinely open question whether possibility 1 is right, possibility 2 is right, or both are right. Personally, I would relatively strongly favor possibility 2. Like people really searched pretty hard for additivity violations, and at the end of the day, quantum information isn't that hard. It's just matrices, finite dimensional matrices. So it's pretty reasonable to think that we'd have found them by now if they existed. They're certainly not guaranteed. Whereas on the other hand, we know very, very little about finite temperature black hole microstates in quantum gravity. So I would lean towards possibility 2 being much more likely to be true. But yeah, I think it's worth both trying to look for these disentangled microstates and trying to look for additivity violations. The people in this audience might be more likely to look for the second than the first, but you can always change fields and look for the first if you want. So yeah, hopefully that was helpful. Thanks a lot. Any questions? I guess.
Thank you very much, Geoff, for a very nice talk. So I think we can thank Geoff. We had quite a lot of questions during the talk, but I think we have time for some more if Geoff is willing to stick around.
I have a question. I don't know how to raise my hand.
Yep.
Okay, so if I understood correctly, one step in your argument that led onto these two possibilities was the idea that you could just so you might have had initially in your narrow energy band some atypical states, but you assume that you can just throw them away, and then you're left with a puzzle. And to me, it's really not clear whether it's so easy to throw them away. Just to give you an example from say you have some bulk dual, say you have type 2b supergravity. And the type 2b supergravity equations of motion, they admit black hole solutions, which might be dual to whatever typical microstates, but they also admit fusible solutions. And I'm not sure in what sense can you exclude the fusible solutions while keeping the black hole solutions. I don't know what you can do.
So what I'm saying is, let's just think about this from a CFT point of view, right? We have some finite dimensional code subspace. Okay, there is some state in that code subspace. Maybe it's a fuzzball or whatever it might be. That has this entanglement entropy that's smaller than A1 over 14. Okay, then just on the CFT side, we can just restrict to a code subspace.
That's exactly what I'm contending. I don't think I think in holography I agree with you that formally you can just restrict to whatever code subspace you might have. It's not clear that any randomly or purposely picked code subspace will have a reasonable gravity dual. And
I'm not wanting a gravity dual of the full code subspace. I'm just saying if let's just think about the code subspace from boundary point of view at this point, right? I'm just saying we can take states within that finite dimensional code subspace and we can throw them away as strict orthogonal complement.
But then you want to use gravity in order to make an argument about how you're computing the entanglement entropy.
I'm using okay. Let me say the places where I'm using gravity to compute the entanglement entropy. I'm using gravity to compute the entanglement entropy of the thermofield double state. I think we're very, very safe in that, right? I hope you would agree. So that's one thing. I'm using it to compute this S of BLBR for the thermofield double state. The only other place where I'm using gravity is with this argument later on, where I want to say that if we have a state which has a bulk interpretation and has a smooth horizon and looks like ADS Schwarzschild outside the horizon, then it can't be a disentangled microstate. That's the only other place where it shows up. But if you don't like that argument, that can be got rid of, and you can just think of possibility 2 as a statement about boundary states within the energy band, the existence of an orthonormal set of them that have suitably low entanglement entropy between the two halves of the band. And then you can just ask the question about what are the bulk joules of those states? And maybe the answer is there's just no bulk joules and it doesn't make sense to talk about the bulk joules at all or something. That's certainly an option, but I think it's still interesting if that is the answer. Maybe the bulk joule is some horrible superposition of different things or something, and maybe that causes RT to break down somehow. I don't know. Again, seems interesting if that's what's happened. But this is just a claim that this set of microstates, if it exists, none of them can satisfy these 3 assumptions.
I see. Okay. I'll think about it some more.
I really in this process of throwing away states, they can be as horrible as they are, right? They're just states in boundary CFT.
But I have a problem thinking because usually I have some consistent theory which is my boundary theory, and I cannot just cherry pick what I want to.
It's an artificial code subspace. It's not that I'm throwing them away from the theory and then still wanting it to be like a CFT or something like that.
So I guess I just need to understand to think a little bit better about the fact that so you claim you actually didn't use any sort of bulk dual, or you just use the bulk dual of states that we all agreed that should have a bulk dual, and then
exactly, and then I constructed this set of states with certain boundary properties, or I said either you have this set of states with certain boundary properties, or you have extensive violations of additivity. And then we can ask about the bulk dual of those states for boundary properties. And maybe the answer is it's truly horrible, or it doesn't exist, or whatever. I'm certainly open to arguing that it's dodge to even consider the bulk dual of those boundary states. But as boundary states, they have to exist.
But then, because it's a bit funny. It's a very artificial construction, right? You start from something that you have. You start with examples of states that have absolutely no problem with your with the additivity assumption, and then you throw away everything that has no problem.
We're just trying to find...
You have a problem.
Yeah, I mean, we're just trying to find, like, for possibility one, we just need to find some channel that violates this thing, right? That channel could be as horrible as you want. It doesn't have to be like a nice channel, a sensible channel. It can,
Okay.
You could take a similar strategy for other channels of just, the throw states away and then until you get a violation. That's a strategy you can take with any other channel. It's just, in this case, if it doesn't work, then you've learned something else instead. You've learned that this set of states exists.
Okay, I think we should give time for some other questions. I think Nick has his hand up first. So Nick.
Yeah, just something went by a little quickly, and I just want to understand, why is it that the disentangled microstates have to have the entropy e to the s, or sorry, number e to the s, I should say?
Yeah. So the point is that the thermophile double state is this super entangled state between two copies of the black hole, right? So let's just say I have my H code. So I have an approximation, 2 copies of H code, and I have some approximations of the thermophile double state built out of those 2 copies of H code. And now I'm gonna throw away one state from H code. So it's gonna go from dimension e to the s to dimension of e to the s minus 1. Okay. What I can do is I can take my approximation to the thermophile double state and just project it into the new H code. Okay, and then basically this is 1 minus the projector onto the state that I threw away, and the overlap between the thermophile double state and any pure microstate in the code subspace is e to the minus s, or the overlap squared. And so by applying this projector onto the orthogonal complement, I've only changed the thermophile double state by an e to the minus s amount. So I still have a very, very good approximation to it. So I can do this e to the s many times before I lose control over my approximation. Okay.
Okay, I think Juan is the next one.
Yeah, so would you say that the state that has the brain behind the horizon has some structure or not?
Yes, I would count that as sorry. I would say the one with the brain at the bifurcation surface. Yeah. Like the Mauticina state, I would count that as having structure at the horizon. So it's really structure at the bifurcation surface, not structure at the. Okay. There's no structure at the horizon up here, but there is structure at the horizon. Yeah, you count the bifurcation surface as part of the horizon.
I mean, could you have some states where there is perhaps a brain behind the horizon, but only at the places where the A1 would. So there was the area A1 that ends at 2 points at the horizon, right?
Yeah.
Maybe you have a brain.
You could imagine just structured. Yeah.
Just there, and then, but in the rest of the interval, you might have some very deep interior, maybe some deeper in the interior. So that's consistent with the.
Again, I would count that as structured horizon. I'd say now you could try making the same argument with a different choice of B, and maybe the set of states you end up with are like different in that case. You need this to be true for any choice of B. So to some degree, like there have to be states with structure at any point on the horizon, but maybe each individual state only has structure at a couple of points of the horizon, or codimension one smaller than one to the horizon subset of it.
Right. Okay, thank you.
So Samir, I think you're the next one up.
Okay. Hi. Yeah. Thanks for a nice talk. I just had a question about something connected to the way we think about black holes in ordinary semi-classical gravity. So the moment you have a horizon, we know we can make this bag of gold structure inside, which has an unbounded number of states. Is that fact somewhere which I can see in these mathematical things you were presenting? Can you make any connection between having a smooth horizon and then being immediately able to find an unbounded number of states at the same energy? Does that show up in your formalism anywhere?
I don't think it's relevant to the arguments that I've made in this talk. I could make comments on what I would say about that, which is just that if you, let's say you have a bag of gold and you put a huge amount of entropy behind the horizon, and then you look at the entropy of the boundary for that state with that huge amount of entropy behind the horizon, then that will be given presumably by the QES prescription. And what will happen is that you'll have some quantum extremal surface sitting near the horizon. And so you'll get an answer that the boundary entropy is actually only the von Neumann entropy of the black hole, even though you thought you'd made something with much, much larger entropy. And so my answer to that would be that even though semi-classically those states in the black bag of gold look all independent, then there's non-perturbative overlaps between them because of quantum gravity effects. And so actually there's e to the minus s overlaps between all of them, and that means that they all actually lie within the same subspace of dimension e to the s. So there actually only were e to the s independent microstates. You just overcounted them. They're an overcomplete basis of states. So we have sort of explicit examples of that in the toy models, like the Copley-Madicina states are a nice example. They're an overcomplete basis that have branes in different states behind the horizon, but like in practice, they all lie in the same e to the s dimension. So that would be my answer to that question. I don't think it matters to anything I've said. And yeah.
Which was the example you cited again? With the example where you have
Copley-Madicina states. So it's you take the SYK model. You take the thermofield double state in the SYK model. So this is sort of dual to ADS2. And then you just basically project the left boundary into some simple state. And you can argue that what that does is that creates sort of a end of the world brane that falls into the bulk here. But this is well behind the horizon. The horizon is here. And so how many of these states do you have? Well, if I have SYK with n fermions, then there's 2 to the n different states. But it turns out that's much bigger at low temperatures than e to the s. But these are all low temperature states that lie within the same e to the s dimensional subspace. They just have tiny little overlaps between each other. So you can argue about the SYK model not being a true theory of quantum gravity, or this not being legit in some ways, but we certainly have, and certainly like the page curve calculations using islands and so on, then that's how they work. If you just consider, like, naively, if I have an evaporating black hole, I let my black hole almost evaporate. So up here, this is some small black hole, but in this interior, I have this huge amount of entropy. Then the quantum extremal surface prescription says, okay, you might think there's all that entropy there, but you actually look for the smallest quantum extremal surface, and it's sitting here. And so actually, the entropy is just the area of the black hole.
Thank you.
Okay, I think we have time for another last question. Nyayesh, I think.
Hey, thanks, Geoff. Very nice talk. Can you go back to your picture of the two identification of the left and right?
This one? Or
oh no, the two identification. That was at the end.
Oh, sorry.
Hartman and
Madicina, yeah.
Okay. There you go. Okay. So it looks like so that's the blue surface, this end of the world brane. It is inside the horizon, but if I have basically modes, let's say I'm talking about perturbations that are analytic throughout the space, that means that for every left moving mode or ingoing mode, there would be an outgoing mode. Is that true?
Yeah, I think that's right. Yep.
So that means that basically by horizons, just basically by imposing analyticity, things reflect off the horizon basically because you agree with that?
Juan can answer this better than me, but yeah, I think if you actually want to consider a quantum state, I think they just were thinking mostly about the classical geometry. But I think, yeah, you would need to impose like reflecting boundary conditions at that end of the world brain. I think that's the right.
I see. Okay, so I guess I just wanted to add that so I talked about this yesterday, that this actually gives you this Boltzmann reflectivity, exactly this setup. If you go to the Rindler coordinates or the Schwarzschild coordinates, so in that sense, this would connect to the echoes picture if it's taken seriously.
But if we look at, what about if we look at some later time? I would have said if we look at a late time up here, this state is not time translation invariant. If we look at a late time up here, then I would have said you quickly lose any echoes or anything like that. Is that right? I think if I look at the late time behavior,
I think
it looks like an ordinary black hole.
No, it's quite. Yeah.
I'm afraid you're breaking up. I don't know if it's my problem or yours.
I'll come out of this picture.
Nyaesh, could you repeat your question? You were breaking off for a bit.
Oh, sorry. Yeah. So no, I agree. It's not time translation invariant. So what this picture tells you that for any ingoing there must be an outgoing mode, but how long it takes for the outgoing mode to get out, it might be a very, very long time.
Yeah, I mean, also, you can have transplanckian problems, right? If I have some mode up here, and the mode up here in the interior, then to evolve this interior partner back in time to then get it coming out, then it seems like it's becoming transplanckian, and so
So then this is the question for you, that if this is not a time translation invariant state, then I mean, don't you expect the black hole to kind of equilibrate to some sort of a thermal equilibrium? So if this is not time translation invariant, this cannot be it. Wouldn't you say that?
No. I would expect all these disentangled microstates to not be time translation invariant on grounds of like general thermalization grounds. If I have some disentangled state with some energy, and then I let it evolve in time, it will become more entangled. Eigenstate thermalization hypothesis says that these things can't be energy eigenstates, so they can't be time translation invariant.
Okay. Well, thanks. Yeah, I think I need to think about it, but it could be that like you kind of keep switching from one to another, and none of them are time translation invariant, but they all look like this.
I mean, if you have an almost complete basis of these states, then well, you won't switch from one to another, but you take one, evolve for some time, then you'd expect to basically be able to rewrite that time evolved state as a superposition of exponentially many other disentangled microstates. But I would say there's just multiple equivalent semi-classical descriptions, but that's maybe a topic beyond the scope of.
Thank you.
Okay, I think we've kept Geoff for long enough. I think we should thank Geoff again for a very nice talk and for answering quite a lot of questions.
Thanks for inviting me to talk.